Okay, in this lecture we're going to work with the laws of sets. What we're going to do is this is going to be kind of algebra of sets. So it's related to the set identities we were talking about in a previous lecture. And basically what our job is going to be is to simplify what you might call expressions or something. I'll probably just have to show us. Okay, so this is what these questions look like. We'll do 3 examples here. So simplify this object using only the laws of sets. These are the laws of sets. Similar story, simplify this, identify the laws used in each step. Simplify this, indicate explicitly which laws are used at each step. Now this is something that will be almost certainly a question in an assessment. And what you have to do is you have to use the law and you have to name, so you have to, of course you have to use the law. You have to use the appropriate law, you can't use the incorrect law, and you also have to name the law that you're using. Okay, now to my mind this is mostly a question of pattern spotting, right? Just noticing, you know, what you've got here versus how it applies here, and practice. So this is my opinion. This is a question that students find very difficult. Okay, so starting with this, P union Q and not P. So we're trying to simplify this. You won't be able to do it in one line, you'll have to use a number of the laws. Okay, so looking at this, what can we use? So if you want, look at this, maybe pause the video and have a think what law you'd like to use on this. Okay, so I'm looking at it, and the only thing it seems to, it's not, for example, like you have to spot the pattern and be precise. It's not absorption. While there's a union and an intersection, it's P and not P. It would have to be P and P, or not P and not P to use that. It's not, for example, associativity, because it's not all intersections or all unions. If you have a mixture of unions and intersections, and these two sets are not the same, what you have to use is distribution, this one. So we're going to have to write this A union Q and not P as P union Q intersection P union not P. So it's a question of practice. So I mean I can write out I will write out the symbols that I'm using here. So let's say ABC. Now you wouldn't normally do this, but just a little scribble, A, B, C. So this is equal to, because look, you have the union and you have the intersection. So the first is A union B, P union Q. You need the brackets, it's very important, otherwise you've got ambiguity. Like for example, is this B intersection A? No, because you have to union with A first. That's the first bit, intersection. And now we have, this looks like A union C here, which is P union not P. And then, so that's using the law appropriately and saying which one. So this is by distributive law. Or by distributivity, something like that. Okay, so now you look at it again and you see, is there anything we could use? And maybe there's something for P or not P. So I have a look here, P or not P. So this is true for any set. So A or not A is the universal set. P or not P would also be the universal set. Now you do need to quote the law, but if you were to just kind of write down that this is the universal set, that wouldn't be bad. So everything is either in P or in not P. But here, if you do it properly, you want to use it and also quote it. So this is P union Q intersection the universal set, and that is called, you can use inverse or complement. I'm going to say by inverse. Actually, I'm going to say by complement. And now have we got something for intersecting with the union? Yes. If you intersect with the union, it makes no difference. So anything intersecting the union is that anything set. So this intersect U is just a P union Q. So this is This is probably one of the most difficult questions. This is what's this called? This is called, it's not called annihilation, it's called identity. So this is a question that people find probably the hardest. My opinion is put some time into this. There's similar questions based on logic with very, very similar laws in semester 2. And if you can get good at this now, it'll help you a lot for semester 2. I would put a lot of time into this. Now, not at the expense of kind of the easier things, like get good at the easier things first, but then definitely spend time on this. Okay. So that's the first question. Now, you can't simplify that anymore. And this is in fact true. You can put any sets in here. You'll get this thing is equal to P union Q. Okay, so let us do a second question. Simplify not, that's what that bar means, not P or Q and P. Identify the laws. So the big thing, again, if you want, have a look at the laws, pause the video, look at this, and pause the video and when I say pause, I suppose, and see what pattern does this have. Okay. So if I'm looking at this, I have a big knot over a union of two sets, and that's exactly DeMorgan's laws. A big knot over the union of two sets. So I need to use De Morgan here. So in terms of the De Morgan, the A and the B, this set knot P is the A, and Q intersection P is the B. Okay, so I'm going to write not. I need to be careful, like you have to see this other knot. So not P or Q intersection P. Now let's see what De Morgan does. So it puts the knot on each of the sets and it swaps from union to intersection. So we're going to have to put a knot on this and a knot on this and turn this union into intersection. So this is not P, the union turns into intersection, and then a knot goes on this set. Okay, and that is by De Morgan. Okay, now we have another look. What about, well, you can have a look, but probably here, like you should understand that not P is P. So think about it for a sec. Something that's not, it's like a double negative. It undoes it as such. So not P is P. If it's not raining, it's raining. If a number is not even, it's even. Okay. So we're going to use something on this. Let's see what it's called. If we got a not here, it is called a double complement. So not A is A, not P is P. And this one is another story where you've got a big knot over two sets, except this time with an intersection. Actually, by the way, you can get from here to here by putting, I think, knots on the A's and the B's. That's one way of doing this. So we're going to use two laws at once here. So not P is the same as P. That's going to be by double complement. And keeping the bracket, De Morgan here, the knots go on each, so you're going to have not Q. Okay. The intersection gets turned into a union, not P. And it kind of looks like the one above now. So this is by double complement. And another De Morgan. Use De Morgan twice. Now here again, you want to stop the video and figure out which laws have we got here. Now again, you might be tempted to use absorption, but look, it would have to be A intersection A, P intersection P. Now you can swap these two. That's called commutativity. There, look, the order of a union or an intersection doesn't matter, but it's still not absorption because you need A intersection A. Here the best you can do is P intersection, not P, so that's not what it is. Okay, so it's actually going to be distributive law again, this one. So it's like kind of multiplying out A intersection B, union A intersection C. A intersection B, union A intersection C. So that's what we're going to have here by distributive law. So I have P intersection, not Q. So it's like that by that, union P intersection, not P. Okay, by distributive law. This time I'm going to write distributivity. Okay, now we look again now. Here it should actually be possible to do this without looking at the thing. What is in P and not in P? Well, nothing is P and not P. That's not possible, because if you're in P, you're not in not P. If you're in not P, you're not in P. So there's nothing in both of these. Now we're just going to need a name for that. So P intersection not P, here it is. A intersection not A is the empty set. There's nothing that's in A and not in A. So P intersection not P is the empty set. And that is called complement law. Okay, so you have P intersection not Q union with the empty set, and this is by complement. Now finally, everything that's in P and not Q or in the empty set, well, there's nothing in the empty set, so this is just going to be this, because the union is all the elements that are in this or in this, and there's nothing in here, so it's just going to be this. Again, we need to find a name for this. Unioning with the empty set, giving you the same thing, is called identity. Okay. And one more question. So again, this is actually very similar to something we've had above. In fact, it's pretty much identical to question 1. So I'm going to leave this as an exercise. Do yourself. I'll just write down the answer down the bottom. I'm fairly confident that the answer is X union Z. X union Z. Okay. So what I'm going to do, there's a section here. So DeMorgan's law is very important. Well, it should be important in programming. So now this isn't quite examinable, but I'm going to just talk kind of quickly through this. It's a further remark to help you kind of understand DeMorgan's law. Now you can read it a bit slower than I go through it, but there's kind of, it's really just explaining different ways of thinking about the union as or, the intersection as and the not as not. Okay, and the relationship between them. Okay, so consider a universal set, an ambient set. Okay, so the collection of objects that we're thinking about. Oh, in each thing we're going to have a collection of objects, something like and, something like or, and something like not. And De Morgan is going to apply in each case. So for sets, the objects are going to be subsets. We're going to take the universal set 1, 2, 3, 4, 5. So the objects that we're considering in this way of explaining De Morgan is subsets of U. Okay, so and note that two objects are contained both in A. Oh yeah, we're going to kind of illustrate De Morgan's laws. Just illustrate, so it's not a proof written, just illustrate, talk about. Take A to be the set 2, 3, 5 and B to be the set 1, 3, 5. There are two objects that are contained in both A and B, the 3 and the 5. We call this the intersection. So this is how this intersection is an and. We can represent the ambient set U as well as the set A and B, and the fact they intersect using a Venn diagram. So here's 2, 3, 5, 1, 3, 5, and the 4 is left out there in the intersection. We can demonstrate for a general A and B where the intersection is. I do this on the next page. Okay, no problem. What is the OR here? Another set that can be formed from A and B is their union. So remember, A and B are 2, 3, 5, 1, 3, 5. The union of A and B, well, the and here is a bit troublesome because you don't want to think about and. Okay, denoted A union B consists of all those objects that are elements of A or elements of B, and it's a non-exclusive OR. So if something is in both of them, yeah, we've seen this before, so I can go past. I actually should skip this bit because we know this bit. Okay, here's just explaining the difference between the OR in everyday language, that is a mathematical OR the exclusive OR. So the question put to a normal person, a mathematician. So something that's, did you have a starter or a dessert? So a normal person, if they had both, would say, I had both. A mathematician would just say yes. So if they have both, the OR is included in that. If you really want, this is something we've seen before, you can think of the union as being all the objects that are in A or in B or in both. So this is a way of kind of thinking like that. Okay. This is obviously the wrong picture because Where's the union? This is not the union. But I'm reasonably happy that you know what the union is. This is not the set, not A. But let's do the union. There we know what the union is. We should have, yeah. It's the mistake. Mistake. So if I just take the shaded region here. So this bit is the A, this is the B, and this is A and B. And the not is the complement. So for example, if the set A is 2, 3, 5, the not of A in that universal set 1 to 5 is 1 and 4. Okay, we know all this. Right, so DeMorgan's laws, and this is what we've seen already, so I'm actually going to skip this. You can read it yourself. Or no, we'll just go through it quickly. So consider all the objects that are in not A or B. So not A or B is 1, 2, 3, 5. Not this is 4. This contains objects that are not in A and not in B. This is the set not A, this is the set not B, and this thing is the same as the intersection of those. So this is a demonstration or an illustration of the first DeMorgan law that says not A or union B is not A and not B. And look again, you see not going on the sets and the union being flipped to an intersection. This is known as DeMorgan's law, and it's always true. Okay, similarly, we have if an object is not in A or B, A and B, so if it's not in A and B, it's either not in A or it's not in B. Okay, right. Another way of looking at this is in logic. Now, I have to be very, very careful talking about logic, and you're going to do logic properly next semester. So, as I said, I have to be very careful, but we're only doing an analogy, so we won't be too careful. So consider all the set of sentences. And a sentence can either be true or false. Now, we won't say what a sentence actually is. So examples, the capital of Ireland is Dublin, true. Wednesday is not a weekday, that's false. 4 is a prime number, false. The word earth contains 5 letters, is true. Now, this is stuff that you'll probably see next semester. So if S1 and S2 are sentences, then their conjugation is the sentence S1 and S2. And the conjugation sentence is true whenever they're both true. And so this conjugation is like an and. For example, if we have A is equal to the set 2, 3, 5 and B is equal to the set 1, 3, 5 and make sentences, 1 in A, I'm going to just call this and, 1 in B is false, because for the conjunction to be true, they must both be true, and 1 is not in A. So this is false. While this statement is true because 2 is in A and 1 is in B. So this conjunction is like and. Or is true whenever one of them is true. And the not is a sentence which is true whenever S is false. So it's like you toggle the truth value. So for looking at A 2, 3, 5, the sentence not 1 in A is true because the sentence 1 is in A is false. So this sentence is false, so its negation is true. And what do we get? Not 1 as an element of A is 1 as not an element of A, and that's true. So the negation is like the not. And then the DeMorgan's laws work like this. So this is saying that the negation of S1 and S2 is the same as the negation of S1 or the negation of S2, where this or is, I don't even remember the name of it, is it the conjunction or this, but it's the or. So this is DeMorgan's law for sentences. So for example, let's see, can we come up with an example? Let's say the sentences are S1 is that it's a Monday, and S2 is that it's raining at this moment. So if it's not Monday and raining, there's only, so if that's not the case, it's either not Monday or not raining. Okay. Another way of thinking about it is actually switches. So you can think of the objects as a collection of switches, and I won't say exactly what a switch is, but I'll just say they can be on and off. So if you combine switches in series, this is like an and. For this to be on, this has to be on, and this has to be on. You can combine switches in parallel. So in this setup, this parallel switch will work if S1 is on or S2 is on or both are on. We're going to call this thing S1 with this funny symbol here. This is the and the or will do with this funny symbol here. And here you consider if you want to, the not is switching the switch off, toggling it. So here we can look at the toggle. So if this is to be off, so this is like toggle. Am I calling it toggle on the next page? Yeah. So if you want to switch this off, now remember, so DeMorgan basically puts the toggle is the not, turning it off or switching it. This is toggle S1. So switch off the first one or switch off the second one. So that's DeMorgan for switches. And similar story if you want to switch this. So toggle S1. Now this isn't examinable, this is just trying to get you to understand DeMorgan's laws. I'll probably put it in as an optional. Well, I can't because the other bit wasn't. Okay, so to turn this off, you have to turn this off and turn this off. So I'm just going to write T for short. You turn off switch 1 and turn off switch 2. Similar story, if this is actually off and you want to turn it on, you have to actually switch that and that. Now that will definitely turn it on for sure. Okay, so DeMorgan's law, that's just what we did there. Yeah, so there's all different ways we can imagine this. There's another one, functions. So functions take inputs and produce outputs. So suppose we're thinking about functions where the inputs are numbers between 1 and 5 and the outputs the outputs are either 0 or 1. So for example, here's a function, calling it f1. Put in 1, you get out 0. Put in 2, you get out 1. 3, you get out 1. 4, you get out 0. 5, you get out 1. Now, why is that? I'm saying this is an example of a function. Now later on we're going to see this notation. So 1 in, 0 out, 2 in, 1 out, 3 in, 1 out, 4 in, 0 out, 5 in, 1 out. A different function where you put in 1, you get out 1. Put in 2, you get out 0. Put in 3, you get out 1. Put in 4, you get out 0. Put in 5, you get out 1. Okay? You can combine, now it says the elements. You can combine, oh yeah, so these are the objects. So you can combine functions in various ways. One of them is the maximum function. So you could take take two functions, combine them, and make a function that is the maximum. So for example, say the maximum function of these two at 1, well, what's the maximum of 0 and 1? 1. So the value of the max is 1. And the max here, so if you put in 1, the maximum output is 1, so you get out 1. Put in 2, the maximum output is 1, put out 1. Put in 3, both the outputs are 1, put out 1. 0, the outputs are both 0, the maximum of them is 0. And for 5, both the outputs are 1, so you put in the maximum, which is 1. And this max is like a union, it's like an OR. I don't know why I haven't got the OR, but it should be there. Similarly, the minimum function, and the minimum function is like an AND. So the minimum, for it to be a 1, you need 2 1s. If it's a 1 and a 0, you're going to get a 0. And if you've got 2 zeros, you're going to get a 0 for the minimum. And then a toggle function that basically switches the value from 0 to 1. And a similar story, a similar kind of DeMorgan's law. So if you toggle the maximum function, you get the minimum of the 2 toggles. So the maximum, this is like a union. This is like a knot. A union is an intersection of knots. And this one is like not a intersection is a union of knots, which is DeMorgan's law.